Hello, good afternoon, everyone in the room. Hello, folks on live stream. If you're watching the recording on YouTube, the algorithm worked. These are the talks you're looking for. Bear in mind that this is part 2 out of 3, and I very much encourage you to watch the talks by my colleagues at this AI Data Infrastructure Field Day, Harry and Robert. We cover the FlashBlade in AI story from different angles. My name is Boris Fagan. I'm a technical director, a software architect with FlashBlade at Pure Storage. Purity FB is the name of the FlashBlade software stack. I want to walk you through some of the internals of Purity FB, cover some of the main architectural decisions that we've made, and more importantly, why we made them. To dive under the hood of the system. I think it's a really cool design, and I'm excited to have this opportunity to share that with you. Before I get into that, let me take just a couple of minutes to set the scene, which will help frame the rest of the talk. Now, let's start here. All data infrastructure is AI data infrastructure, or it should be AI ready, since AI is no longer a niche technology; it's mainstream, and data is very much at the center now. For storage, of course, the value of storage has always been vested with the data, but what AI has done is supercharge this basic premise, because we know that quite literally and in various technical senses, better data and more data means better AI. So our technical challenge is to remove barriers, because if your data is over here, but your AI infrastructure that's capable of processing it is over here, that's not useful to anyone. Conversations about AI data infrastructure often focus on one or two specific axes. For example, GPU utilization. Now, what do you need for high GPU utilization? Well, you need the system to be reliable. You need it to be high performance. Yes, of course, these are really essentially the same metric. Reliability simply says remain up as much as possible, and high performance says do as much as possible to keep the GPUs fed while you're up. The question is this on its own sufficient to run AI workloads in production today? And it's not by a long shot. Now, let's take performance, for example. Performance is, of course, a means to an end. So you might have an excellent RAG setup, but if it doesn't comply with your organization's policies around data retention or data protection, its effective throughput is zero, irrespective of what it's on the paper specifications. Similarly, for such a rapidly evolving field, performance has to be predictable, and it has to be there for a range of workloads and for a range of scenarios. Now, similarly for reliability, I mean, yes, of course, the system has to be reliable, but it should also be efficient, both in terms of storage efficiency, and I'm talking the classical definition of storage efficiency, which is the ratio of usable capacity to raw capacity for your growing data sets and the intermediate products that your AI pipelines are producing, but also in terms of power efficiency. Since any watt of power that we can shake loose, so to speak, from on the storage side is another watt that you can put towards GPUs, or is perhaps something that you can pocket as savings on your energy bill. And of course, again, right in the center of it all, this has to be straightforward to adopt. So it has to work with the customer's existing environment, and it has to be straightforward to expand as they figure out what works, as they scale up the workloads that do work. So the overall message here is that even in the most HPC-like of storage environments, of AI environments, really, you still need enterprise features if you want to run in production. Now, it won't surprise you when I say that FlashBlade S does all of these things. We have a rich set of services. We have native high-performance implementations of several protocols, including, of course, NFS over RDMA for GPU Direct. We have a number of data protection features. We have snapshots, replication. That's not really what this talk is about. I won't go into the features specifically. What I really want to get into is what's under the hood. So what we'll do is we'll start from the inside out. You can see a picture of a FlashBlade chassis there. We'll cover the hardware briefly, then we'll move on to what the very basic services in the software stack look like. We'll pop up into the major modules, and then we'll spend a bunch of time talking about load balancing across the system. You know, how do you extract performance out of this? So a FlashBlade cluster consists of one or more chassis. The chassis is our largest building block. Within a chassis, you can have up to 10 blades. Each blade carries a CPU complex, a bunch of memory, a network interface. Each blade can host up to 4 DFMs. DFM is a direct flash module, and to a first approximation, a direct flash module is a pure built, pure designed SSD drive. The major difference being that due to our vertical integration between the hardware and the software, we can extract efficiencies. There's power efficiencies, storage efficiencies, performance out of this that are simply not possible with an off-the-shelf SSD. So consider this, that we're not building a drive, right? So we should have the right layers of abstractions for a storage platform, not for a drive. And so you can see that the building blocks are very modular. They're granular, which means that you can expand the system as you progress on your AI journey, as you figure out what you need. Now, there's one really cool architectural property here that I think highlights the kind of co-design of the software and the hardware. I said at the beginning that data is at the center, and you might say, well, what does that even mean? So you can take a FlashBlade cluster, and over time, you can expand it. You can add more blades. You can add more DFM modules, these SSD equivalents. You can remove DFM modules. Perhaps you're going through capacity consolidation. And over time, you can end up with a system that shares no hardware components with the system that you started out with. And yet, it is the same cluster. It is the same system. The data is still there. You did not need to take downtime for this. You did not need to reconfigure the clients for it. So it is very literally about the data rather than any particular piece of iron that happens to be there at any given time. And of course, that's a real advantage in a rapidly evolving environment.
Question.
Oh, yes.
What's the minimum config to get started? Because I see 1 up to 4
yes.
SSDs in a DFM. How many blades do I need to get started?
You need 7 blades with 1 DFM each.
So 7 blades with 1 DFM.
Yep.
Okay.
Yep. All right. Okay. So enough about the hardware. Let's talk about the software. So Purity FB, as I mentioned, is our software stack. There is the most important takeaway here is that Purity FB is really an internal environment for building protocol implementations. It's not really specifically an implementation of any one protocol. It's a number of building blocks for building a storage platform. Now, Purity took a conscious decision to invest in these frameworks early on, and it has paid off handsomely. So FlashBlade initially launched with support for the NFS v3 protocol, and over time we saw and we predicted the growing adoption of fast object, and we implemented a native object stack, a high-performance object stack, SMP, NFS over RDMA. All of that sits fundamentally on the sort of bedrock of machinery. Now, I want to get into the big modules and load balancing. I'll just call these out quickly. I could hold forth for a long time, so I'll just do it briefly. So there is an asynchronous programming framework to extract the most out of CPUs. This is a distributed system, so things have to talk to one another. There's a low latency internal transport that runs over Ethernet. This is a heavily optimized subsystem. We use techniques like zero copy. We do bypass of the operating system kernel. We talk directly to the network interfaces on the blades to get the most out of it. Load balancing we'll talk much more about in a second. We have a scalable metadata engine with support for distributed transactions, and both of these are designed to support a large number of clients, driving a high rate of change in the system. And indeed, our data protection features, such as snapshots and replication, are backed by this. So Purity FB is really a toolkit of machinery that we put together in different ways to implement different protocols and different data services. So what's inside a blade? So on the right, we have a picture of an actual FlashBlade S blade. On the left here on the slide, we have a conceptual diagram of the software layers that run on that blade. I drew the diagram first and then realized that actually it maps on perfectly to the geometry of the blade, which is really handy for this slide. We need somewhere to store the data. So the direct flash modules, the DFMs, are on the bottom in the diagram, and you can see the enclosures in the picture on the right. Then we pop up. You can see the CPU complex and the DRM on the right. On the left, we have our compute layer. The most interesting thing about this compute layer is that it is not monolithic. It is broken up into these compute partitions. We call them authorities, but think of them as compute partitions. Now, ignore the exact number that are on the slide here. There could be more, there could be fewer, depending on the configuration. And we'll come back to that in a second. But the intuition that you want to take away from this is that...
Hang on, Max, did you have a question?
Question?
Yeah, I do have a bunch of questions because I'm sorry to be a bit brutal, but we've seen the blade stuff when your colleague was presenting before.
Mm-hmm.
And just a couple of things. So first of all, there's going to be, in fact, 3 questions. Are you going to talk about FlashBlade S versus FlashBlade E?
Mm-hmm.
Are you going to talk about zero-move tiering? Are you going to be talking about AI? Thanks.
Yes, so I should have mentioned this. I will be talking about FlashBlade S. I won't be talking about zero-move tiering that we announced in the last couple of days. And what I want to show is how the load balancing that we do, especially for those who haven't seen it, gives you that performance that you need in AI. Any other questions? Okay, so moving on from the compute tier and going up into the endpoints. So we have the endpoints are effectively a layer that are responsible for parsing the transport protocol and the storage protocol. So this is the layer that understands TCP, the layer that understands RDMA, and you can see that it sort of corresponds to the where the midplane connectors go, which are the blade's route to the outside world. Now, so conceptually, you might say, well, a request would enter on top through the endpoints, make its way to the compute tier, and then be serviced with data from the DFMs. And this is nearly correct, but remember that we actually have a bunch of blades. So what happens here is that these are really planes that stretch across the cluster. So we have an endpoint plane, we have a compute plane, and we have a storage plane with the DFM. So while the hardware resources are partitioned into blades and chassis and DFMs, we have these logical planes that effectively represent the totality of that kind of resource. Now, that decoupling away from the hardware of the blade, what it gives you is, or a neat property of it, and I'll tell you in a second, the thing that it enables is that each one of these compute partitions, they are not tied to running on any particular blade. Similarly, the persistent state that's associated with one of these compute partitions is not tied to any particular blade or any particular DFM. It's spread through the cluster. The state of the cluster is vested in the DFMs. Now, you might ask, why would you go and virtualize the compute layer? The reason is that it enables a terrific thing, which is that a compute partition can migrate from one blade to another. So let's say, for instance, if you're scaling up your, let's say your inference workload, you're adding more blades. As soon as you plug those blades in and you introduce them to the cluster, we're able to put a bunch of compute partitions on those blades and make use of that extra CPU and that extra network and that extra DRAM. And if you're familiar with VM migration that hosting providers use to, say, do maintenance on the hardware or do expansions, load rebalancing, this is conceptually very similar, except, of course, the compute partitions here are specialized to our use case. So this decoupling, this virtualization, is a central pillar of that expansion story, of that upgradability story.
So when we say compute partition, logical, so what you might be doing is separation of cores, right?
In fact, no. This is the compute partitions. Think of them as logical entities. They don't have a direct tie-in to any particular blade or any particular core of a blade. They're very much like I imagine perhaps a virtualized controller. And then you can figure out how to map it onto a blade, and within that blade, how to map it onto the resources of that blade. So they're logical rather than physical.
Got it. So it's like a compute container.
Effectively, yes.
Which gets mapped, which is told to run on a particular hardware resource.
Correct, yes.
But then the question is that mapping dynamic or it is static?
It is dynamic. It is dynamic. Yes, absolutely. So thank you for the question. It is absolutely dynamic. So as the system is running, when you add a bunch of blades, we're still running. There's no disruption. We're going to right then and there take a compute partition, tear it down wherever it's running, and boot it back up on the new resources that have been provided. It is totally dynamic. There is no tie-in from that partition to any blade.
So, but then if you do that, you lose all the locality of cache of the previous resources where that compute partition was running.
So we find that in practice that rehydrates pretty quickly, and that doesn't affect
that gets amortized by the time that you are running compute partition on those particular resources, though it is dynamic, and that dynamism is only related to when the resources are added and removed.
Correct.
Which is kind of a rare occurrence, so that you get more amortized time.
Yep, absolutely. Yes.
To be okay with that performance that you would be throwing off of the caching.
Indeed, and in most cases, there isn't really like the amount of time that it'll take to rehydrate the cache won't, like as you say, it won't really affect your overall kind of profile.
Right.
And you have to redistribute the storage endpoints as well.
So the storage endpoints are thank you for the question. They are entirely stateless. So there is no state whatsoever in these endpoints, which means that once that blade...
There's certainly software state. There's certainly like TCP connections.
True, correct. Yes, you have to redistribute the TCP connections across the endpoints. You don't need to redistribute the endpoints themselves. Okay. Yes, you're right.
To distribute loads.
So I'll actually get to the networking layer in a couple of slides. Is that okay?
That's fine.
Okay. All right. So now that we've...
One question, mapping this architecture, this flexibility to the hardware that you were showing.
Yes.
So this is across the cluster. And what's the notion of a cluster? In cluster, you can have multiple 10 blades, right?
In the cluster, you can have multiple chassis, and each one of them has 10 blades. So you could have 20, 30, 40.
And this is blades. Across clusters?
This is within a cluster. This is within a cluster.
Okay.
Yep. Across.
But we can have multiple exposures because now I can imagine between those 10 sitting within a cluster that the latency of moving from one to the other is really low because it's the same chassis with one backplane probably then.
Yes. Yep.
But how do you do with the second enclosure then? What's the backplane at that moment? You need an insane amount of bandwidth at that moment, low latency?
Actually, we're fully interconnected in terms of bandwidth, like speeds and feeds between the chassis. So when you're connecting multiple chassis together, we have two external 400 gigabit switches that we call the external fabric module, which gives you the oomph to go and do that.
Okay, so it's 400 gigabit switch.
Yeah.
Okay.
I'm going to skip ahead a couple of slides here, because I think this gets to your point of why are you even doing this? How does it help me?
Yes.
Okay. So the ability to rebalance compute partitions across the cluster is about expandability, your upgrade story, your expansion story, making use of the hardware. Then how does that come into play with an actual workload? So with an actual workload, what we do at the protocol layer, first of all, is we take a protocol namespace, and I'll come back to that in a second, and we then distribute it across the compute partitions. So each compute partition is responsible for a subset of that namespace. So for example, let's say that you have a file system, and that file system contains training data, or perhaps it contains some intermediate products in the AI pipeline. It would be a bad idea to map that onto any particular blade in the system, any particular compute partition in the system, because as you're putting more and more data into that file system, and as you're increasing the performance requirements on that file system, you want to engage the full capabilities of the array. That's what this is really about, basically scaling with your needs. And this, together with the balancing of the compute partitions, is what allows us to do that. So we first map. I promised to explain what a namespace is. Let's take, for instance, the space of inodes in NFS, or the space of file offsets. If you have a large file, then the offsets within that file form a space that we can partition. We break it up into ranges that then map onto these compute partitions, each of which is going to manage data layout, background operations, GC, metadata compaction on their own, and they're going to run on different blades, which gives you the performance.
So how do you partition inode space? Like, for example, NFS, the way it exports itself is through a directory structure. And what happens is that now mapping this to application, what can happen is that different training jobs can have different namespaces.
Yep.
And also a single training job might need a lot of parallelism within itself as well.
Absolutely.
Versus across jobs as well.
Yes.
So
absolutely. So if you have, let's say you have a training job that's accessing a ton of files, so it needs a throughput for that. So those files are going to get mapped out across the partitions, which means that as you're accessing different files, you're going to engage more of the cluster. I will, unfortunately, I'm really short on time, so I'm going to speed to the next slide, and all I'm going to say is that this workload distribution continues through into the DFM. So first we map to compute partitions, then to the DFMs. For instance, if you have a large file that you're doing training on, you don't want one or two DFMs to become the bottleneck for that. So we want things to be nice and uniform, so we distribute them across the.
And this works for all of your different storage protocols, not just NFS.
Yes,
okay.
Absolutely. Yes, all of them are implemented natively. All of them are using this underlying technology.
Okay, because it's like not too many AI workloads are going to be sitting on top of an NFS.
Yep. NFS over RDMA is actually quite popular, but it does work for object as well, certainly.
Okay, so that's important. So object as well, indeed. So object is in here as well.
Yes.
Okay.
Absolutely. All of the protocols are benefiting from this underlying kind of internals. I think I maybe dove too deep too quickly, but yes, absolutely.
Okay.
This is what's happening.
You answered it. Thanks.
Thanks. And then the final bit is that you might say, well, okay, how do there's going to be complex client configuration. how do I actually tap into these internal load distribution mechanisms? And this is where our network comes in. So as I mentioned, if you have multiple chassis, you're going to have these two outboard switches. If you have a single chassis, you just plug directly into the chassis. So there's a few connections that plug you into the array. And then on top of that, what we do is we virtualize, in effect, the IP of that storage cluster. Now, what that means is that from a client's perspective, you specify one IP, and we're going to distribute the connections across the blades in the system. And once we do, the internal load distribution mechanisms are going to kick in and do multiple compute partitions and multiple DFMs. So we do the load distribution for you effectively all the way from the front door all the way to the DFMs to allow you to scale. And this absolutely works for all the protocols.
Can I as a user specify that, okay, I want to do training for this particular job, and that job, and I want like n number of parallelism, so it should map to n number of compute partitions. Is that configurable from the user's perspective?
So what we're trying to do really is to remove all of that complexity from the user and handle it very much internally. So once you start submitting load, we're absolutely going to light up the entire array to handle your workload, to avoid you having to worry about it. And that's all I had. The results speak for themselves. I will thank you very much for your time. And I encourage you to watch the presentations by my colleagues, Hari and Robert, as part of the same AI data infrastructure field day.